Yes, all right, class. A very good morning, everyone. Very good morning, everyone, and welcome to the session. Welcome to the, signal and system revision session on DFT. So, yes, guys, the electronics and communication examination is coming closer. That is coming Saturday, 15th of February. And looking into, electronics and communication paper, DFT is one very important topic. Almost every time producing a question, good question, okay, 2 mark question. Okay, so that's why it's important, if anybody writing the EC paper, to definitely have a go through of this topic. Okay, good morning Manasvi, good morning Madhu. All right, so quickly keep updating all your friends that the session is now live, and let's get started and let's learn the DFT, the discrete Fourier transform. Okay, where we are going to have a revision, okay, the complete revision of the DFT, okay, with important questions. Okay, with important questions, where I'll target a lot of PYQs also in today's session, because I told you almost every year there has been, and if you talk about recent years, I would say, if you say, recent, 10 years paper, almost every year, at least 9 out of 10 years, you see a DFT question. That's how frequent it is in the EC examination. Okay. So let's have a go through of this one, and I'll take up some good PYQs also to be discussed in the session. In fact, let me also tell you that the instrumentation paper has been already conducted on 1st February, and there is a question, okay, on DFT, DTFT and DFT, the link between them, okay, in the paper, right? All right, so very good morning everyone. Once again, let's quickly get on moving ahead. Okay, so the online live course, guys, for GATE 2026 and 27, if you are interested to join that, the batch, fresh batch, just started 8th February. Okay, and the fee for 1 year, that is GATE 26, is 19,999. For 2 years, it is 28,999. Okay, and if you are waiting, okay, eagerly to join directly at Hyderabad Center offline, the first regular offline course for GATE 26 for EE and EC starts 24th of February. The fee, which is currently priced at 54,999, and you can also get some add-on advantages if you belong to, IIT and ITs or state government colleges, triple ITs, or if you are any of the previous OM student as well, right? So moving ahead here, and let's consider first of all xn, okay, be a finite length sequence. And when I define xn as a finite length sequence, suppose the length being n, say for example, if I write down any signal here, okay, what is the length of the signal? This is what I mean, the number of samples from the first non-zero sample to the last non-zero sample, and that is equal to 4. The length is 4. Okay, the length is 4. We also call it as Lx, and we'll call here as n. Okay, right. And when I'm taking a signal of length 4, okay, I will start the signal from origin, that is, this should n equal to 0, 1, 2 and 3. Okay, so that means considering any signal xn which is outside this interval, that means within this interval, first of all, within this interval, what interval? The signal is defined, not only it has the length n, but it also is defined only from origin to n minus 1. Okay, where it can take any value. I don't specify anything here. It could take any value in this interval, but yeah, outside this interval, the value of the signal is 0. Okay, so it has the length n. Okay, that is number 1 point. Okay, right. So considering a finite length signals, because again, if you want to, talk about the Fourier transforms of the discrete signals to be processed using computer, first of all, it must have finite length so that you can, input that particular signal to a digital machine. Okay, now, next important thing is DTFT. Okay, what is the DTFT and what is DFT? See, today's session is majorly about DFT, discrete Fourier transform. Okay, but just like CTFT, you normally first discuss the DTFT, discrete time Fourier transform, okay, of the discrete time signals. Okay, so when you talk about DTFT, discrete time Fourier transform, okay, just like the CTFT, we represent DTFT as, of course, summation, okay, summation xn in general, okay, minus infinite to infinite, summation xn e power minus j omega n, where the DTFT, okay, which gives the frequency information of a discrete time signal, which talks about the frequency spectrum. Okay, here this frequency is continuous in nature. Okay, so guys, we'll not go in much depth of the theory today because we need to revise quickly with examples. That is what is the target. Just 5 days left for the examination. But yeah, the overall important points you must know, okay, that when you talk about DTFT, the frequency is continuous in nature. Okay. And again, we need to sample the frequency. We need to discretize the frequency, and the Fourier transform, okay, which is also discrete in frequency axis, okay, which is obtained by sampling the frequency, okay, will be a DFT. Okay, so when you talk about what is the concept of discrete frequency, because this is continuous in nature, okay, how do I discretize the frequency? What is the concept of discrete frequency? What is the concept of discrete frequency? So I will define the discrete frequency here. Let's say the discrete frequency is omega k. Let's say the discrete frequency is omega k. So what is the idea now? Any DTFT, one more important point is any DTFT is always a periodic function. Any DTFT is always a periodic function having a period of 2 pi. What does it mean is, okay, since the omega is continuous in nature and it is continuously spread over a period of, over a period of 2 pi. That is, it can take any value from the interval minus pi to pi. And if you write down the IDTFT formula, if I here write down the IDTFT formula, okay, the xn is then represented as 1 upon 2 pi integral over one time period x omega e power j omega n d omega, where this integral, as I told you, is for one time period, or suppose one time period I take as minus pi to pi. Okay, because any DTFT is periodic with the period of 2 pi. Any DTFT is always periodic, and that too with a fixed period of 2 pi. It is necessary and sufficient. It is necessary as well as sufficient to have the information of any DTFT for only one time period, that is minus pi to pi. And hence xn is written as 1 upon 2 pi integral minus pi to pi x omega e power j omega and d omega, right? Okay. Now I was about to define the discrete frequency. Okay, dear, what is that discrete frequency? What is the idea of the discrete frequency? See, if you know DTFT and if you know the concept of discrete frequency, you can write down the DFT formula. So see, I represent a discrete frequency, suppose omega k. What we basically do is, any DTFT which is, continuous in frequency, continuous over a range of 2 pi, it can take any frequency over the range of 2 pi. Okay, so the total range 2 pi. Okay, what we do is, what was the length of the signal? The signal was having the length n. Okay, when I say length n, or suppose length 4, it has total 4 samples. Okay, from the first to the last. From the first non-zero to the last non-zero. If a signal has n length, or I'll say like that, if a signal has n points in the time domain, we will define its Fourier transform also having n points in the frequency domain. That means I need to define n specific set of discrete frequency, and to define it, what I do, I take the total range of frequency 2 pi, I divide by n, okay, and then I multiply k here, okay, where k is any integer from 0 to n minus 1. So that means if I start putting the value of k, what are the discrete frequency you get? 0. Then next would be 2 pi by n. Next would be, if you take k2, so it becomes 4 pi by n. Next is 6. So these are the specific set of frequencies, okay, up to the n minus 1 times 2 pi by n. Okay. So if a signal in time domain has length n, in the frequency domain also it will have the length n. That means it will be having n number of frequencies, and those n number of frequencies are defined by this formula. The discrete frequency omega k equal to 2 pi by n into k. Now that means when I write down, okay, when I write down the DTFT, okay, suppose what was the DTFT? DTFT was, let me rewrite x omega, okay, summation xn e power minus j omega n, okay. Okay, now, if this was the DTFT, what is my DFT? DFT, as I told you, is the Fourier transform obtained by discretizing the frequency. Okay, so it is a function of not omega now, omega k. Okay, but omega k depends on what? 2 pi constant, n is the length of the signal constant. What will vary here is k. K can take any value 0 to n minus 1. That means this DFT or this Fourier transform is now actually a function of k. For different values of k, you get different omega k. So we simply write it as xk, x of omega k or xk, given by what formula? Summation. Now see, I told you, signal also has length n, defined from n equal to 0 to n minus 1. So limit also changed. Okay, summation n equal to 0 to n minus 1 xn e raised to the power minus j. Omega will become omega k. So writing down the omega k value, 2 pi by n into k, and then into n. Okay, that is what is the DFT formula. So DFT is the Fourier transform obtained by replacing the omega by the discrete omega. In short, I'm telling, okay, let's make it as a quick revision session. Okay, so this is what is the DFT formula now. Now let us write down this formula. What is xk? It is the DFT of xn, summation 0 to n minus 1. Keep going through summation 0 to n minus 1 xn e power minus j 2 pi by n into k. Now we will also write down this formula normally in terms of twiddle factor. I'll come to it. In the DFT, k takes the value 0 to n minus 1. K will take the values from 0 to n minus 1. Similarly, when I write down the IDFT formula, IDFT xn will come out to be 1 upon n summation k equal to 0 to n minus 1 xk e power j 2 pi by n into kn. Okay, where n again is 0 to n minus 1. Okay, so this is the basic introduction of the formula of DFT and IDFT. Now, let's talk about this twiddle factor, because both of them involve the, e power plus j 2 pi by n or e power minus j 2 pi by n. Okay, where e power minus j 2 pi by n is constant because n, the length of the signal, is constant. So what will I do? Let's say the wn e power minus j 2 pi by n be the twiddle factor, and if that is the twiddle factor, this is the twiddle factor, which in a sense mathematically also represents the nth roots of unity. Okay, placing down the DFT formula in terms of twiddle n, in terms of the twiddle factor. So what do I get? The DFT will be given by summation 0 to n minus 1 xn w power kn. Summation n equal to 0 to n minus 1 xn w power kn, right? And IDFT formula will be summation 0 to n minus 1. Oh, I'm so sorry. 1 upon n is the missed factor here. 1 upon n summation k equal to 0 to n minus 1 xn w power minus kn, right? W power minus km, right? Okay. So these are the DFTs and IDFTs formula in terms of twiddle factor. Now, if you take up the twiddle factor, okay, what is the twiddle factor? As I just told you, e raised to the power minus j 2 pi by n. Okay, now if you try w power k and w power k plus n, or basically if you separately write down only w power n, if you only separately write down w power n, so power will multiply, and what you are only left with e power minus j 2 pi, e power minus j 2 pi cos 2 pi minus j sin 2 pi cos 2 pi 1 sin 2 pi 0. That means it is equal to 1, right? So w power k can be written as w power k plus n, isn't it? That means because w power k has w power k plus n, so similarly because of this, dear, because of this, x of k plus n can also be written as xk, because xk depends on what? Xk summation x and w power kn. So if w has a repetition pattern, xk will also have a repetition pattern, and similarly xn also. So both DFT and IDFT are periodic. Both the DFT and IDFT, just hold on for a second here, just hold on. Okay, yeah, sorry. Okay, so what I was telling is, because of the repetition in W, the DFT and IDFT are both periodic with the period of n. Okay, with the period of n. Okay, and it is again sufficient to compute the results only for one period, that is 0 to n minus 1. Okay, so remember that. Let me rewrite the DFT x of k and x of k plus n will be same. Similarly, IDFT x of n and x of n plus n will be same always. Okay, will be same always. Okay, now let's understand these formulas more for a 4-point DFT. Okay, so what is 4-point DFT? N will be 4, and if n is 4, what is W4? W4 becomes e power minus j 2 pi by 4, and that is equal to e power minus j pi by 2. Now open the formula. E power minus j theta cos theta minus j sin theta. So what is cos pi by 2 is 0. Sin pi by 2 is 1. So what is left is minus j. That means W4 value, okay, the twiddle factor value for n equal to 4 will be minus j. Okay, why I am starting with 4 points separately? Because 4 point makes the most common, if a direct calculation anytime required, 4 point makes the direct and the important case. Okay, so if I write down the formula of the DFT x of k, okay, it is summation xn W4 power kn from n equal to 0 to n minus 1, that is n equal to 0 to 3. That is what n equal to 0 to 3. Clear, everybody? That is n equal to 0 to 3. Now, let us open up this formula. Now, what is the range of k in the DFT? In the DFT, the range of k is also 0 to n minus 1. That means the range here is 0 to 3. The range here is the 0 to 3. So, if I take up the value of x0, okay, what is the value of the x0? The x0 now, if you take x0, if you take k equal to 0, w power 0 will be 1. W power 0 will be 1. So, it is only summation of xn. Summation of xn means it is only x0 plus x1 plus x2 plus x3. Okay, if I talk about x of 1, what is the x of 1? X of 1 is given by summation n equal to 0 to 3 xn. Okay, now what is w? Okay, if you want, I'll place down the value of w, no problem. So, k is 0 to 3, but before that, let me place down the value of w. So, this is summation n equal to 0 to 3 xn w. Now, w as I calculated, w4 is minus j, so minus j power kn. Anyways, first value k equal to 0, so w power 0 was 1. Now coming to k equal to 1, and it becomes then minus j power n, because I have put k equal to 1. Now open up the value, dear. Okay. What will I have? N equal to 0, x0 minus j power 0 is 1. Then minus jx1, right? Minus j power 1. Next will be minus j power 2. Minus j power 2 is j square, but j square is minus 1. Okay, so minus of x2. For n equal to 3, minus j cube, minus of j cube you solve will become plus j. So plus j x3. Okay. Similarly, x of 2, n equal to 0 to 3, x of n minus j power 2n. But minus j power 2, if I solve separately, what is minus j power 2? Minus j square is j square, but j square is minus 1. J square is minus 1, so this can be further written as summation of the xn, j square as I told you is minus 1, okay, and then power n, this power n, summation 0 to 3. Okay, and that is going to be how much? Put down n equal to 0, the first is x0, okay, then n equal to 1, so minus of x1, then n equal to 2, so plus of x2, n equal to 3, minus 1 power 3, again negative, so minus of x3. So alternate plus minus pattern, okay, and x of 3 is summation n equal to 0 to 3 x of n minus j power 3n. I'll put k equal to 3, and when I open this, what you are going to get here is, you are going to get the first one, of course, as x0. Okay, first one, of course, as x0. Then you will get plus j x1. Okay, then you will get plus of x2. Sorry. Then you will get minus of x2 and then minus j of x3. You can open up for minus j power 1, minus j power, minus j power 3 and minus j power. Or first you can write down minus j power 3 itself has j power n. So j power n will open actually. Okay. Anyway, so these are the results, and normally we can arrange these results in the form of a matrix. Okay. So if I collect, okay, suppose I have the signal xn whose DFT is taken. What is the signal xn? x0, x1, x2, x3. This is the DT signal. Okay, this is the 4-point DT signal. x0, x1, x2, x3. And I am trying to calculate the 4-point DFT. Okay. That means I am trying to calculate x0, x1, x2 and x3. x0, x1, x2 and x3. So what is this equal to? Okay, so x0 plus x1 plus x2 plus x3. First is simply addition of all. So I write down 1, 1, 1, 1. Next is what? x0 minus j x1. So what should be the entry of the second row? 1 minus j, 1 and minus j, minus 1 and plus j. So see here, x0 minus j x1 minus x2 plus j x3, minus x2 plus j x3. Second, x2, x0 minus x1 plus x2 minus x3. All alternate plus minus, 1 minus 1, 1 minus 1. 1 minus 1, 1 minus 1. And last one, x3, okay, the coefficients are 1 and j, minus 1 and minus j. 1 and j, minus 1 and minus j. Okay, right. So this is what is the twiddle factor matrix. This is what is this matrix will be known as the twiddle factor matrix. We name it as W. Okay, simply W, that is the twiddle factor matrix, and we write down any DFT x of k as the W matrix x of n, or simply we write this operation as capital X being the DFT is given by W into x, small x being the time domain signal. Okay, small x being the time domain signal. So what should be the IDFT? Okay, IDFT xn in this sense is given by inverse of the matrix, okay, W inverse xn, okay, or we simply write it this way, okay, the small x is W inverse of the W inverse multiplied by the capital X. Okay, now that means to calculate IDFT, I need the inverse of the matrix, and usually inverse, especially for a 4 cross 4 matrix, will take time. Let me tell you one direct property, that this given matrix W, this matrix W is orthogonal in nature. It is orthogonal in nature. Okay, what is the orthogonal matrix? Okay, it will satisfy the property W transpose equal to identity. W into W transpose equal to identity, and if W into W transpose is identity, okay, you can shift the W on the other side to W transpose is W inverse, or inverse of the matrix equal to the transpose of the matrix. That means this calculation is now simple. Let me rewrite this. Okay, so what is the small x? IDFT is actually W inverse into x, but it can also be equal to W transpose into x. It can also be equal to what? W transpose into the x. It can also be equal to the W transpose x, and transpose everybody can do it within seconds. It is just exchanging the rows and columns. So what is important is, okay, noting down this 4 cross 4 W matrix, twiddle factor matrix. Okay, so this is what is the twiddle factor matrix. Okay, W, okay, for a 4-point DFT. Okay, for a 4-point DFT. See, first row, now, I'll talk about some simple points here. First row, that is x0, okay, will always be 1, and central alternate plus minus. Actually, let me take you towards this property, and in fact, you notice the third. Okay, sorry, not the third, fourth and second. You notice the relation between fourth and second. Okay, see, I'll talk about this one. This corresponds to k equal to 0. K equal to 0 means all ones will be there, and this corresponds to k equal to 2. Okay, this is k equal to 2, that is x2. Okay, k equal to 2 here is n by 2, because I have talked about the 4-point DFT, and whenever you talk about n by 2 point, it will be alternate. Always in any matrix, it will be alternate plus minus. Alternate plus minus. Especially if you talk about these two. Okay, the second row and the fourth row, they are nothing but conjugate of each other, isn't it? Okay. So first row is simple all ones. Okay, then the third row is simple alternate plus minus. Only second, if you remember, okay, 1 minus j, and that to first two elements, if you see 1 minus j, rest is sign change, minus 1 plus j. Then, okay, the fourth row is nothing but the conjugate of second, isn't it? 1 is 1, the conjugate of real number is same. Minus j becomes plus j, minus 1 is minus 1 only, but j becomes minus j. So all conjugate, all complex numbers are taken in the form of conjugate. Okay, so this is alternate plus minus pattern to be followed in the second and fourth row. Actually, there are two important properties. Let me take you towards that property before we conclude and before we solve any question also. Okay, what is that? What is that? What is that? Two very, very important properties. There is a list of properties. Okay, but yeah, two very, very important properties. Number one is here. Okay, the central ordinates. Okay, and the first ordinate as well. Okay, the first, not only central, but first and central, both I am going to talk in this property. What is the first ordinate? That is x0. What is x0? Capital X0 is summation of xn. What do you mean by summation of xn? Summation of xn means x0 plus, or only addition, all plus, x0 plus x1 plus x2 plus x3, okay, plus whatever be the length of the signal, plus x4, etc. till xn minus 1. Okay, but if you talk about x of n by 2, this is the central ordinate where k equal to n by 2. Okay, this corresponds to k equal to 0 and this corresponds to k equal to n by 2. That is given by summation minus 1 power n into xn always. And when you open this minus 1 power n, okay, for n equal to 0, minus 1 power 0 is 1. But for n equal to 1 or any n equal to odd, minus 1 power odd will be negative. So minus x1. Then again, minus 1 power even will be plus. So now plus will come, next odd, so minus will come. So this is alternate plus minus, as I told you. Here what you have to simply follow is the alternate plus minus. x0 minus x1 plus x2 minus x3 plus x4 minus x5 and etc. till the last value. The alternate plus minus. These are very important properties, useful for questions. Okay, the first order, the first and the central ordinate. The first and the central ordinate. At the same time, if there is a signal which is a real signal, see, now let's also talk about symmetry property. Let's also talk about the symmetry property. What is the symmetry property? If xn has the DFT xk, x conjugate n, that is the conjugate of the signal, will have the DFT x conjugate minus k. X conjugate minus k. That means if a signal is real, what do you mean if a signal is real? These two are equal. The signal and its conjugate is equal. Okay, then their DFTs should also be equal. So x conjugate k should be equal to xk. X conjugate minus k, should be equal to xk. Or x minus k should be equal to x conjugate k, or x conjugate. I'll write it more clearly. See. Okay. X conjugate minus k is xk. But what is x minus k then? I'll shift the conjugate on the other side. Can be written as xk whole conjugate. Let me write it this way. Okay, let me write it this way. But we know that the DFTs are periodic. Okay, so again, let me, write it in the reverse manner only. Easy for understanding. Okay, let me take this result. What I am writing here is x of k is given by x of minus k star or conjugate. Okay, star or conjugate. Okay, so because DFTs are periodic, with what period? Period n. So x minus k is also equal to x minus k plus n, right dear? X minus k plus n, or I can write it this way, x of n minus k plus n whole bar, right? So any xk can be written as x n minus k whole bar. Now, you see, if you talk about n equal to 4, if you talk about a 4-point result, okay, see, for 4-point result, you first calculate up to x2. Okay, you calculate up to x2, calculate up to central ordinate, and then you don't have to calculate anything. Why? Because what is the value of x3? The value of x3, as per this conjugate symmetry property, we can write this as x of 4 minus 3 whole conjugate, and that is x of 1 whole conjugate. That is what I have shown you in the calculations also. Okay, the x3 is equal to conjugate of x1, the fourth and second row were conjugate of each other. That is in general true whenever the signal is a real signal. Clear everybody? Okay, so x3 is conjugate of x1. So x3 is not to be calculated, it is just conjugate of x1. There is a symmetry. Okay. If I explain you with respect to n equal to 8, first understand here. Suppose if n equal to 8, okay, have a look into it. Suppose if n equal to 8, then what can I say? If n equal to 8, okay, so see here again, any x of k will be written as x of 8 minus k whole conjugate, and what you have to first do is calculate up to central ordinate. What is central ordinate? x4, that is n by 2. Calculate up to n by 2. Okay, then what is x5? Okay, 8 minus 5, 3. So conjugate of x3. x6 conjugate of x2. x7 conjugate of x1. That's it. This much is important. Note these three. Okay, that means if you already have calculated x3, x5 is not required. x5 is conjugate of x3. x6 is conjugate of x2. x7 is conjugate of x1. There is a symmetry. Symmetry about which line? Symmetry about the central ordinate line. Okay, symmetry about the central ordinate line. Okay, 3 and 5 not equal but conjugate of each other. That is why I call this property as a conjugate symmetry property. Okay, the values on left and right are not exactly equal but equal to the conjugate of each other, right? Good morning, Sarvanan. Okay, they are equal to the conjugate of each other. Clear everybody? Okay, similarly 6 is equal to conjugate of 2 and the 7th value is conjugate of x1. Okay, about which line? About the central ordinate line. So you can simply call it as a mirror, a conjugate mirror rather. Okay, and the values around this are related by conjugate of each other. That means you don't have to do any additional effort to calculate this. If you know the values of the left, those are automatically calculated just by taking a conjugate operation. So these are two important results. Okay, one is central ordinate property and one is the symmetry. Okay, also in symmetry, 1 or 2 points I'll add on. If a signal is real, see what is first I told you. What is the first I told you? Xn if real, if only real, then what is xk? Then xk is conjugate symmetric. Then it is conjugate symmetric. If xn is real and even, xk is also real and even. If xn is real and odd, xk is pure imaginary and odd. Clear everybody? These are same like these are the properties applicable in the regular Fourier transform also. Okay, so if a signal is real and even, Fourier transform also real and even. If a signal is real and odd, Fourier transform is pure imaginary and odd. Pure imaginary and odd. Okay, so and then central ordinate and the first ordinate. These are some important properties, and then we'll go through some more properties. This is about symmetry. Now, for a moment. Okay, like I just explained you symmetry line. Now, what is the symmetry line? So let me explain you. Okay, circular folding also. Okay, then we will go to the questions. Okay, let me explain you the circular folding property also. Okay, now if xn is the signal, dear, if xn is any signal, x minus n mod n is the representation of the circular folding. Circular folding is the folding around, not deriving it but just telling you the quick result. It is the folding about, once again, the n by 2 line, the central ordinate line. Okay, it is folding about the n by 2 line. For example, suppose I'll take two examples here, a 4-point signal and a 8-point signal. Let's understand both. Suppose I take a 4-point signal. Okay, my question is, what is x minus n mod 4? What is x minus n mod 4? So understand here once again. Okay, Okay, so xn, what is the range of n? Okay, what is the xn value and what is going to be x minus n? I will write down the xn values with respect to n. So n is 0, 1, 2, 3. Okay. Now, what is the xn values given to me? 2 and minus 1, 3 and 5. And what is n by 2 here? Since I have taken a 4-point signal, okay, so this becomes the n by 2. Okay, and as I told you, n by 2 will be the mirror line. Okay, so how do you take the mirror image? Normally for any signal, you take the mirror image about y-axis. I'm asking you to take the folding or take the mirror image about the n by 2 line. This is the n by 2 line. Okay, so there are two values around this. Okay, so this value will come here. I'll write down the x minus n value. Now see, origin is not going to be disturbed. Why? See logically also. Because x minus 0 is same as x0. So there is no effect on the origin value. This is as it is. You separate this actually. Okay, then, okay, this is the mirror. Mirror value will be same. Only thing is values around the mirror will be swapped. Around the mirror, this will come here and this should go here. Okay, so answer is 5 here and minus 1 here. So what is the x minus n answer? What is going to be the x minus n answer if I write down the sequence now? This is what is known as circular folding. X minus n mod 4 is equal to 2 and 5 and 3 and minus 1. Okay, so you just have to take the image about the n by 2 point. This is the n by 2 point. Okay, and since this is the mirror, okay, the mirror will be at the same position. Only thing is values around the mirror will be swapped. So 5 comes here, minus 1 goes here. That's it. Hope it is clear. And if it is clear, you should be able to answer this question for me. So suppose if I write down a signal xn, which is equal to something like this. what should be the value of x minus n mod 8? X minus n mod 8. Circular folding. I'm just explaining circular folding right now. So what should be the value of x minus n mod 8? What should be the value of x minus n mod 8? Okay, so let's write down. Let's write down to see what are the values of n. If I again write down n here, this is origin. 1, 2, 3, 4, 5, 6, 7. This is the important one. This is n by 2. Because if it is n equal to 8, so n by 2 becomes 4. N by 2 becomes 4. So this is the n by 2 point. Correct? This is what is the n by 2 point, which is equal to 10. Origin will remain as it is. Now, the value at the mirror is 10. Okay, then whatever is to the right will come to the left. Now, you have to create the reflection about the n by 2 point. You have to fold the signal about the n by 2 point. Okay, so what will happen? 6 minus 3, 4, which were to the right, respectively, they will go to the left. 6 minus 3 and 4. Then, what is there to the left? 3, 0, minus 1. Now, they will appear to the right. First 3, then 0, and then minus 1. This is what is the answer. Okay, 2, 4, minus 3, 6, 10, 3, 0, minus 1. Right, dear? This is what is x minus n. Okay, fine. Next case then. Okay, this is x minus n mod 8. Okay, so what is the circular folding property on the DFT? So if xn has the DFT, if xn, let me write this way here, separately let me write down the xn data also. So if xn, where is that case gone? Sorry, here it is. If xn has the DFT xk, x minus n will have the DFT x minus k. So this property is like regular Fourier transform only. If there is folding in time, there will be folding in frequency. There will be folding in frequency. Okay, just a second here. Okay, yeah. Right. So that is what. Okay, if there is folding in time, there is folding in frequency. I'll take a relevant question here. Okay, I will also take a relevant question here. Now, coming to the time shifting property, but again, since xn and xk are both DFT, are both, periodic. So again, for periodic signals, we know that we have a circular time shift rather than the linear time shift. What is the circular time shift? Property is same. See, property is same as what you have learned for regular Fourier transform. Like if I take you towards DTFT. Okay, in DTFT or even in CTFT, what is the property you learn? That if there is a shift in time, there is a, okay, if there is a time shift, there is a phase shift in the Fourier transform. There is a phase term, there is a phase shift, there is a exponential term that will appear here. That is x of omega e power minus j omega n naught with the same sign, e power minus j omega n naught. Okay, but only thing is when you talk about DFT, the frequency is discrete in nature. So if you want to talk about DFT, what you do, you convert omega to omega k, x of omega k, or we simply write it as xk, correct? E power minus j omega k n naught. Okay, e power minus j omega k n naught. So that is xk e power minus j omega k. Omega k means 2 pi by n. What is omega k? I have told you 2 pi by n into k and then multiplied by n naught. See, this is the property I have written here, xk. If xn has the DFT xk, x of n minus n naught n, or n means mod n, is having the DFT xk e power minus j 2 pi by n k n naught. Clear? Okay, and vice versa. Vice versa. If there is frequency shift, there is an exponential term in the time domain. That we know. But what shifting here? What is circular shifting? I'll again take an example here. Okay, suppose if I write down first a 4-point example. Okay, if I ask you x of n minus 2 mod 4, okay, this is what I mean by circular shifting. So, normally what is xn minus 2 here? I'll explain you very simply. I'm not deriving this circular shift, but at least the result you can write down very, very clearly. Okay. Right, A, B, C, D, 67 as far as I am able to say, it's going to be a good rank for sure under 200, but I suppose it would be under 150 or, below 100, not a guarantee. Okay, below 100, not a guarantee. Okay, because few questions were very simple for EE. Okay, but at 67, I guess under 200, I think it is sure, but most likely under 150 or maybe possible under 100. So you can, under 150, you can call it as safe. I think under 150, you can call it as safe. But it could be under 100 also. Okay, because let's wait for the complete paper and the response of the students to come up. Okay, but under 150, I think is very safe. You can consider yourself as very safe. Okay, at this particular marks. Okay, at this particular marks. I'm telling you what? I'm telling you the safer result. I'm telling you the safer result. Isn't it? Okay, just a second. Okay, fine. Yeah, let's move ahead here. Let's move ahead. So what is n minus 2? Normally, what do you do? Where I was onto the circular shift. When I say n minus 2, a linear shift, you will right shift the signal. N minus 2 means right shift. But here, you have to keep, the point is entire signal is always in the range 0 to n minus 1. So since you cannot right shift, you cannot go outside this window. So last two samples, how many samples to be shifted? 2. The last two samples, because they cannot go right, you will circularly rotate and bring them to the beginning. Okay, that means, and in the same sequence, 3 and 7 will come up here and then 1 minus 1. Okay, 3 and 7, okay, will come up here. 3 and 7 will come up here. Clear, everybody? Okay, or vice versa, if I asked you, what is x of n plus 1? Okay, left shift. Okay, so circular left shift. So this signal, which cannot go outside this bracket, will go to the left. So that is why I call it as circular shifting. That is why I call it as circular shifting. So what will come up here? See, these three will left shift. The signal starts from minus 1, 3, 7, and then this 1. Okay, this one appears to the last. That is what I mean by circular shifting. Clear, everybody? Okay, clear. So if this is clear, let me write down one example here as well. Let me write down one example here. And if I want you to write down x of n minus 3 mod 8. So what it should be? N minus 3 means right shift. Okay, right shift means, okay, the last three, how many last three should be right shifted, but you cannot go outside the bracket. What will you do? These last three samples, you will circularly rotate and place it in the beginning. Okay, in the same sequence. In the same sequence, that is 12, then 4, then minus 5. Okay, and then write down 2, 0, minus 1, 3, and 11. Hope this is clear. Hope this is clear to you. This is what I mean by circular shifting. Clear? Okay, this is what I mean by circular shifting. And rest property of DFT I already explained you. Circular shift, oh no, the time shifting again produces an exponential term. This way you can remember easily. Because we know that in any Fourier transform, what is the effect of time shifting? Time shifting gives a phase shifting in the frequency domain. That is the exponential term e power minus j omega n naught, omega replaced by omega k. What is omega k? Discrete frequency formula you must remember separately. So what is that omega k? 2 pi by n into k. 2 pi by n into the k. Okay, so that is what is the property written here as well, and vice versa. If there is a shift in frequency, there is a phase shift in the time domain, exponential term in the time domain, though that I am writing here, circular frequency shift property of the DFT. The circular frequency shift property of the DFT. So what it is? Okay, xn has the DFT xk. Okay, then x of k minus k naught. Okay, just like DTFT. Okay, suppose, again relate with DTFT so that you remember easily. Xn has the DTFT x omega. Okay, so if you write down the DTFT x omega minus omega naught, okay, then the signal in the time domain correspondingly is e power j omega naught n. frequency shift, and opposite sign in the frequency shift. Okay, omega minus omega naught here gives e power j omega naught n. Okay, for which Ashutosh Yadav, can you elaborate what is the doubt, for which one you want another example? Okay, so now when you want to convert this to the discrete frequency, that is DFT. Okay, so suppose the DFT is xk and minus k naught. Okay, minus k naught. Okay, so what will be omega naught equal to? See, normally what is omega? Omega is 2 pi by n into k. So omega naught corresponds to the amount of shift you have given, k naught, 2 pi by n into k naught. So I will write down here e power j 2 pi by n into k naught into n into xn. This should have the DFT xk minus k naught. This is exactly what is written. Okay, this is what exactly written. Okay, what is written? Okay, right. So yeah, we'll take more questions, Ashutosh. Okay, for previous one, if I elaborate one more case, suppose if you want to, for this example, if you want to write down x of n plus 2. Okay, and then we will take another questions once I go to the question area. Suppose if I take x of n plus 2 mod 8. So what is n plus 2? Okay, circular left shifting. What do you do in circular left shifting, dear? These two. Okay, which should be left shifted, but there is no space on the left. Think like this, so they will go to the end. Okay, rest will left shift. Rest will left shift means the signal starts from -1, 3, 11, and then 12, and then 4, and then -5, and then 2, and then 0. Okay, clear everybody? Okay, this is what is circular shifting, and then we have the circular time shift property of the DFT. Okay, the circular frequency shift property of the DFT, circular folding property I already explained you, symmetry also I explained you, some more symmetry results I have taken, first and central ordinate property I explained you. Okay, convolution in time, once again, convolution in time is multiplication in frequency, but here again, because we are talking about periodic signals, so convolution also will be circular convolution, linear convolution. Same sequence, Shiv Prasad, same, see, what 2, it is 2, 0, na? I clearly specified same sequence. Let me go to that example here. Okay, 2, 0, 2, 0 in the same sequence. In the same sequence. Okay, Shiv Prasad. Understand like this. Suppose if you only do n plus 1, think like this, Shiv Prasad, how you will understand. Shiva Prasad. If you suppose do only 1 unit shifting, so what will go? Only 2 will go. Only 2 will come to the last. Okay, if you do only 1 shifting, okay, the signal starts from 0 and 2 will come to the last. Now do one more. What is n plus 2? Plus 1 plus 1. Now you do one more. So now when you do one more, this 0 will go to the last and rest will shift to the left. So what is the sequence at the last? 2, 0. Na? That is why I am telling same sequence. Whatever is there, copy it here. Here also 2, 4, minus 5. 12. 12, 4, minus 5, same. 12, 4, minus 5. Same I have placed here. Okay, so same sequence I clearly specified, right? Okay, yeah. So where we were? Circular convolution. Okay, so convolution in time is multiplication in frequency. Xn has the DFT xk, Hn has the DFT hk, Xn circular convolution, Hn has the DFT xk into xk. Okay, now how do you solve circular convolution? Okay, right. How do you solve circular convolution? Property is same as regular Fourier transform. Convolution in time, multiplication in frequency, or multiplication in time. Suppose there are two signals x1 and x2n. The DFT will be given by 1 upon n circular convolution of x1k with x2k. Multiplication in time is convolution in frequency, and convolution in time is multiplication in frequency. But again, because of periodicity, we are talking about circular convolution. Linear convolution will not converge here. So how do you solve the circular convolution? I'll take two examples here. Suppose you take xn and hn. Okay, let me take two signals, xn and hn. Okay, let me only solve first. Okay, let yn equal to x of n convolution hn, linear convolution. Okay, linear convolution. Okay, linear convolution. How do you solve the linear convolution between these two? How do you solve linear convolution? Because they are both finite in length, and for finite length signals we follow the sum by column method or the tabular method. or any other method that you know. Okay, but if you have followed any of my previous classes, I call it as sum by column method or a tabular method. How do I draw the table? Okay, what type of table I'm talking about? I'll take a table first, okay, where any one signal, because convolution is commutative, you can swap to any one signal, 1 and 2, minus 1 and 3 on the top, and any other on the side. You can swap these as well. You can exchange them. Now, what is the first row? We write down the elements of the top to be multiplied by this first element 4. So 4 into 1, 4 into 2, 4 into minus 1, and 4 into 3. Then all the elements of this top multiplied by 0 and write down the answer from 1 unit right. Okay, go 1 unit right. Okay, so 0 into 1, 0 into 2, 0 into anything is 0. Now next multiply by 1. So 1 into 1, 1 into 2, 1 into minus 1, 1 into 3. Last multiply by 2, and again every time keep moving right. Okay, 2 into 1, 2 into 2, 2 into minus 1, and 2 into 3. Clear? Okay, so what is the net result? What is the net result? This is equal to 4, this is equal to 8, this is equal to minus 3, this is equal to 16, right? And then this is equal to 3, this is equal to 1, this is equal to 6. Correct? Perfect. Okay. Okay, so this is what is the linear convolution. This is what is known as the linear convolution. Okay, now, firstly, I have solved a linear convolution. Now, for the same two signals, let me try to do it here only. Okay, now let me define Z of n is equal to X of n circular convolution. So, convolution symbol enclosed inside a circle, that is a circular convolution symbol. What you will do, you will follow the same tabular method, same sum by column method. I'll tell you only the change. Let me take the same two signals, 1 and 2, minus 1 and 3, 1 and 2, minus 1 and 3, and the other signal I'll write on the side. You can swap them also, as I told you, 4 and 0, 1 and 2. One and 2, minus 1 and 3, 4 and 0, 1 and 2. Now see the results. Okay, 4 into 1, okay, 4 into 2, 4 into minus 1, 4 into 3. Same. Now 0, 0, 0, 0. But I told you, when you talk about DFT and IDFT, okay, especially periodic signals which are defined from n equal to 0 to n minus 1, always there is the boundary. Okay, that boundary, what is that boundary? N is 0, 1, 2, 3, and as I told you, you can't go outside the boundary. Okay, what we do, I told you second row in the convolution is right shifted by 1. So what type of shifting we follow here for periodic signals? Circular shifting. What type of signals we follow? Circular shifting, isn't it? Rather than linear shifting. So what is circular shifting? This was a regular linear right shift. But what we do in circular shift, any one sample which is going out, okay, will be circularly shifted and come up here. So this 0 should be written here. Clear? Now see the next. Multiply by 1. So 1, 2, minus 1, 3. Multiply regular. First do the regular multiplication. But whatever are the two signals right shifted, you have to do the circular right shifting. That means in the same sequence, minus 1 and 3 will come up here. Last. Multiply by 2. So 2 into 1, 2 into 2, 2 into minus 1, and 2 into 3. Okay, and these three samples which have gone out, 4 and minus 2 and 6. Will come up in the beginning. Clear? And now do the sum by column. Now again add the entries of every column. So if I keep adding, okay, so 4, 8 minus 1, this is 7, and 11 and minus 2, 9. This is equal to 7 and minus 4, 3, and this is 16. Clear, everybody? 7, 9, 3, 16. Okay. Okay. If they don't have, you can convert them of the same length. Shiv Prasad. Okay. So this is what is the concept actually. This is what is the concept. The answer is 7, 9, 3, and 16. Check the answers, Ashutosh, once again. This is what is the final answer coming up for Zn. Okay. One more thing you see here. One more thing if you observe here, dear. One more thing if you just observe here. Okay. This particular column. This particular column and this particular column, okay, is exactly the same. is exactly the same, isn't it? These two columns are exactly the same. Yes, Shiv Prasad, zero padding. Okay, this is exactly the same. Okay, that means the value of what signal? The value of the signal Y3 is equal to the Z3, and it is always going to be, because up to the last column, all entries are same. Nah? This is the last column, all entries are same. Okay, what the change is, these values which are going outside this bracket, outside this window, they come to the beginning, right? Okay, so Y3 and Z3 are equal, or in generally the last sample, that is Yn minus 1 or Z of n minus 1 will always be same. Y of n minus 1 or Z of n minus 1 will always be same. Clear, everybody? Y of n minus 1 and Z of n minus 1 will always be same. This is what is important. Okay, the last sample, whether you do the linear convolution or circular convolution, I'll show you on this simple point. There is a 2-mark question in GATE. I'll show you on this very simple point. There is a 2-mark question in the GATE. Okay, I'll take you towards that question. Okay, we are almost done with the properties also. Okay, next is Parseval's theorem. I will take a question onto it separately. Okay, that talks about the energy of the signal. Energy of the signal in time domain, summation 0 to n minus 1 mod xn square is also in the frequency domain. It can also be calculated by the formula 1 upon n summation k 0 to n minus 1 mod of xk whole square. I'll take a question onto it separately. And last is the duality. What is duality? See, I'll write it this way. Duality. The DFT pairs are also dual in nature. If xn has the DFT xk, then capital Xn, okay, converting it to the time domain function. Okay, in duality, we normally think this way. What is the Fourier transform of a Fourier transform? DFT of DFT. So Xn has the DFT xk. Again, if I now convert it to the time function by putting k equal to n, now again, this is the time function. Again, it can have a DFT. What is the DFT of this? What is the DFT of this? It is given by n small x. Take the small x original signal and replace n by minus k. So n x minus k, that is what is written there as well. Okay. Right? Which matrix method, Ashutosh? I mean matrix method for DFT. I have not asked to calculate any DFT right now. That the previous question was just convolution question. We have not done any DFT calculation. Okay, na? Okay. So this is what is duality. Of course, we'll take questions onto it. But one question, let me take you directly towards that simple question first of all. That simple question first of all. Where is that simple question? Where is that? Yeah, here it is. Look into this. A GATE 21 2 marks question. A GATE 21 2 marks question. Okay. So consider two 16-point sequences Xn and Hn. Okay, there are two 16-point sequences Xn and Hn. Let the linear convolution of Xn and Hn be Yn. Okay, so what they are telling, Yn is the linear convolution of Xn and Hn, and Zn denotes the, okay, now Zn is equal to what? IDFT. Zn is the 16-point IDFT of the product of the DFTs. Now see, a small twist in the language, nothing more. A very small twist in the language. What is a twist in the language? Okay, Zn is equal to what? Zn is equal to IDFT, 16-point IDFT of the product of the DFT, 16-point DFTs of Xn and Hn. So what is the Xn and Hn DFT? Suppose Xk and Hk. Okay, the DFTs are suppose Xk and Hk. What is Zn? It is the IDFT of Xk, Hk. Now it is on the circular convolution property, nothing but it is on the circular convolution result. See, what I have told you, if Xn has some DFT Xk and if Hn has some DFT Hk, what they are telling, Xk and Hk multiplied, multiplication in frequency will occur when there is convolution in time. So Xn circular convolution Hn will have the DFT Xk, Hk. So what is the IDFT of Xk, Hk? So now you can tell now what is the IDFT of Xk, Hk? The IDFT of Xk, Hk is Xn circular convolution Hn. Clear, everybody? Xn circular convolution Hn. So see, what is Yn? Yn is the linear convolution now, and Zn is the circular convolution of Xn and Hn. Okay. The values of k for which Zk equal to Yk. So I told you now, already I told you that Z of n minus 1 is equal to Y of n minus 1. The result of linear and circular convolution for the last column will always match. Last column means the n minus 1. Last column means the n minus 1. Okay, so here, since n is equal to 16, okay, so z of 16 minus 1, that is z of 15, and y of 15 will be same. Okay, so for what value of k? Zk equal to yk, for k equal to 15, my answer is D. Is that clear, everybody? Okay. This is what the answer should be, 15. Clear, everybody? This is what is the answer, 15. Done? Simple question. Okay, simple question. Okay, just one result of circular and linear convolution. Also the circular convolution DFT property. One more similar language. Actually, I'll take you towards that language. One more very similar language I'll show you. One more very similar language I will show you. Where is that language? Okay. Here is that. One more gate question. I'll show you this gate question first of all. Have a look into it. Okay. Consider two real sequences with the time origin marked by the bold value. Okay. These were the bold values. I think here they have not come. Okay. This is bold 1 and this is bold 1. That means both the signal starts from origin. Now let x1k and x2k be the 4-point DFTs of x1n and x2n. Clear? Let x1k and x2k be the 4-point DFTs of x1n and x2n. Another sequence x3n is derived by taking the IDFT of this one. Again, similar language. That was gate 21. This I've taken gate 15. So that is why we suggest you solve PYQs. At least language, the model of the question, not 100% same, but you will at least have a lot of practice, enough practice to attempt any further questions also. Okay. So what is this? Okay. IDFT of this signal x3k. Okay. So, when these two are multiplied, that will only happen when there is convolution in time. x1n, circular convolution x2n, that will have the DFT x1k multiplied by x2k. Okay. So what is the IDFT of this one? Okay. If this is x3k, okay. So this signal is x3n. So what is the IDFT of x3n? Okay. The IDFT, the inverse DFT of x3k is some signal x3n. What is that x3n? The circular convolution of x1 and x2. So it's a question on circular convolution. x1 and x2 are given. Can we solve the circular convolution between them? Why not? Can we solve the circular convolution between the two? Why not? Let's do it. If we can solve, let's do it quickly. Okay. So what is that circular convolution? Any one signal I'll write here, 1, 2, 3, 0, and any one on the side. That is, the other one is 1, 3, 2, 1. Mark this as my boundary, and now I'm solving it. 1, 2, 3, 0. Then multiply by 3. 3 into 1, 3 into 2, 3 into 3, and 3 into 0. The value going outside, I'll shift back inside. Now multiply by 2, one more unit, right? So 2 into 1, 2 into 2, 2 into 3, and 2 into 0. This 6 and 0 will come up here, and then multiply by 1. So 1 and 2 and 3 and 0. 2 and 3 and 0 will come up here. 9, 8, 11, 14. 9, 8, 11, 14. Okay, what is the value of x32? Okay, what is the value of x32? What is this time? We know that this time is 0, 1, 2, 3. Okay, so this is n equal to 2 and this is the value of x32. What is the value of x32? Sir, answer is 11. The value of the signal x32. To convert to NAT question, they asked you any specific value. That is x32 and the answer is 11. Answer is 11. Correct. Yes, Shiva Prasad. Correct answer 11. Yes, Varun, it was a circular convolution. Okay. So that is what these language, if it is clear to you, I hope, you will be able to deal with lot variety of questions. Okay. Before I show you some more PYQs, let me go towards a regular calculation question first, which is here. Okay. Now let's take up this question. So consider there is a signal xn 2, 1, minus 1 and 3. Find the DFT. First is DFT and then some properties are there. First only the DFT of xn. Okay, what is the DFT of xn? 4-point DFT. So what I will do for 4-point DFT, we'll use this 4-point twiddle factor matrix. Okay, 4-point twiddle factor matrix. So what is that 4-point DFT? Suppose the DFT is xk. Okay, suppose the DFT is xk and I calculate xk again by that 4-point DFT matrix. So this is a regular calculative question. Okay, so as I told you, what is that 4-point matrix? What is that 4-point matrix? Okay, first row 1 1 1 1, third row alternate 1 minus 1. Okay, first ordinate and central ordinate. First ordinate all 1, central ordinate. Okay, alternate plus minus. Then I told you only second row to be remembered, and remember only first two elements. I'll write it here. Okay, what are the first two elements? 1 and minus j. And then change the sign, minus 1 plus j. Then fourth and second row are conjugate of each other. So 1 is 1, minus j conjugate will be plus j. Minus 1 is again real, plus j conjugate minus j. And then write down the signal here as the column vector. 2 and 1, minus 1 and 3. Okay, so see now what is going to be the first result? Okay, what is going to be the first result? I'll write down the result here. Okay, 2, so first is just addition, 2 plus 1 minus 1 plus 3, 5. Okay, then let's go to this alternate plus minus pattern. 2 minus 1, again minus 1 and minus 3. So 2 minus 1, 1, minus 1, 0, minus 3. So here minus 3. Then next here, 2 minus j. 2 minus j plus 1 and plus 3j. So what is the answer? Net answer 2 minus j plus 1 plus 3j. So 3 and plus 2j. I'll write down the final result. Okay, what I got? 3 and plus 2j. Now dear, if this is 3 plus 2j, no need to solve this multiplication separately. Even if you solve it separately, you will get 3 minus 2j. That's what I told you. Second and fourth row will be just conjugate. So here the result is 3 minus 2j for sure. Okay, 3 minus 2j for sure. Okay, it's a simple matrix multiplication that you can deal with. Okay, so what is my first answer? Okay, my first answer was the DFT of xn, which is xk, and that is written in front of you as 5, 3 plus 2j, minus 3 and 3 minus 2j. Okay, next calculation. Let's go to the next question. So what is that next question? Have a look into the next question. Find the DFT of yn equal to x of n minus 2. X of n minus 2 mod 4 to be specific. Okay, n minus 2 mod 4, right? Now see, okay, so circular shifting. So you don't have to see, there are two things you may think. Okay, the signal xn, I will do the circular folding first and I will again recalculate the DFT. Why to do the recalculation of the DFT? We will apply the circular time shift property. So second question, dear, that if xn has the DFT xk, then x of n minus 2 mod 4 will have what DFT? As I told you, circular shift property, xk multiplied by the exponential term e power minus j omega n naught. That means xk, omega will be omega k here, e power minus j omega k. What is omega k? 2 pi by n into k. What is capital N here? 4-point signal into n naught. N naught means 2 here. N naught means 2 here, the amount of shifting. Clear? Circular time shift property. Nothing but the circular time shift property. So this is finally equal to 2 to 4, 4 and 4 cancel. So it is equal to xk multiplied by e power minus j pi k. What is e power minus j pi k? Let me simplify it further. It becomes cos k pi minus j sin k pi, where k is only an integer. Where k is only integer. So because k is integer, remember that k is a integer. Okay, so integer means sin pi, 2 pi, 3 pi, 4 pi, all of them are 0. Okay, but okay, cos k pi. So cos pi is minus 1, cos 2 pi is again 1. Okay, so alternate plus minus. It will be actually given by minus 1 power k. For any odd k, answer will be minus 1. For any even k like 2 pi, 4 pi, 6 pi, answer will be plus 1. Okay, so what is the final answer? It is simply minus 1 power k into xk. Okay, so let me say that this signal is yn. Yn is x of n minus 2. Okay, now let me come up here. Okay, y of n, if it is x of n minus 2, x of n minus 2 mod 4, what is yk? What is the DFT yk? It is given by minus 1 power k into xk. Minus 1 power k into the xk. Xk is the previous question answer. 5, 3 plus 2j, minus 3 and 3 minus 2j. Correct? Correct. So now multiply by minus 1 power k respectively. Okay, so 5 into minus 1 power 0 will be 5 only. Minus 1 power 1 will be negative. Okay, this is k 0, 1, 2, 3. No? The next minus 1 power 1 negative. So this value will become negative. Minus 3 minus 2j. Minus 1 power 2 positive. So this will remain minus 3 only. And then minus 1 power 3 again is negative. So minus 3 plus 2j. I have multiplied minus 1 power k inside for corresponding value of k. For the corresponding value of the k. Okay, dear? For the corresponding value of the k. So 5 minus 3 minus 2j minus 3 and minus 3 plus 2j is what is the last answer. Is what is the last answer. Hope that is clear to you. Okay, next question. Find the DFT of yn equal to x minus n. Folding in time is folding in frequency. Okay. Okay, circular folding property. Third. Okay, as I already discussed, if xn has the DFT of xk, x minus n mod 4 will have the DFT x minus k mod 4. Okay, so what is the xk? See, xk we have obtained. Xk we have obtained. The value of xk was 5, 3 plus 2j, next was minus 3, am I correct? Yes, and then 3 minus 2j. Okay, now they say, let the signal yn be equal to x of minus n. Let the signal yn be equal to x of minus n mod 4. So what is the yk? So yk, x minus n DFT is x minus k. Circular folding in frequency domain also. And how do you do the circular folding? Circular folding is done about the n by 2 point. About the n by 2 point. So what is k? 0, 1, 2, 3. K is 0, 1, 2, 3 and this becomes the n by 2 point. This becomes the n by 2 point and you have to fold about the n by 2 point. Okay, this becomes a mirror, origin as it is, and the values around the mirror will be swapped. So first 3 minus 2j. Mirror as it is and then 3 plus 2j. This is the answer to this question. This 3 plus 2j goes here, 3 minus 2j comes here because this is what is going to be your mirror. Right, dear? Let me know in case of any doubts. Let me know in case of any doubts. So that is the third answer. Okay, fourth. Find the DFT of yn equal to x of n by 2. Expansion, time expansion. Okay, so I'll explain you the time expansion property now. See, in general, what is the expansion property? I think I did not revise it. See, if xn has any DFT xk, okay, then x of n by m. No compression property, only time expansion property. X of n by n, it has the DFT x of k replicated m times. The same DFT replicated m times. That means if I talk about x of n by 2, it will have the DFT xk. How many times? 2 times. Xk and xk. Now let's understand with this question. Okay, let's understand with this question. So what do I have? Okay, I already have calculated xk. I have calculated xk, that is 5 and 3 plus 2j minus 3 and 3 minus 2j. These are the calculated results. Now the question says that suppose yn is a signal x of n by 2 expansion. Okay, expansion. Okay, x of n by 2. Then what is going to be yk? What is going to be yk? It is nothing but xk. That's what, replicated 2 times. It has to be xk. Okay, that means whatever xk we calculated, 5, 3 plus 2j minus 3 and 3 minus 2j. Replicate it again. Write down again means 5, 3 plus 2j minus 3 and 3 minus 2aj. This is the answer. Because expansion will also make the signal as a 8-point signal. Originally the length was 4. Expanding by 2, the signal becomes a 8-point signal, and here is the 8-point DFT. For any n-point signal, we have the n-point DFT. Done? So this is also complete. This is what you do in the time expansion property. Okay, fine. What is the next part of the question? Fifth. Yn, find the DFT of Yn, Xn convolution, circular convolution Xn. So circular convolution, just like we took other questions on circular convolution. Fifth one is on the circular convolution result only. So what is that fifth one? Yn is x of n, circular convolution x of n. So what should be yk? What should be the DFT? Convolution in time is multiplication in frequency. What is xn DFT? Xk. Again same signal xn, so again the DFT xk, and these two will be multiplied. Xk into xk means what? X square k. Xk into xk means what? X square k. So answer is x square k. Okay, so what is x square k? See, what is xk first of all? Let me write this xk once again. It was 5, 3 plus 2j minus 3 and 3 minus 2j. So what is yk? It is xk multiplied by xk, that is x square k. So 5 square 25. What is the square of 3 plus 2j? I'll write down separately here. Okay, so 3 plus 2j whole square, a square. Okay, 3 square. Then 2j square will be minus 4 because j square is negative, and plus 2ab. So 3 to 6 into 2, 12, 12j. Okay, so this is how much? 9 minus 4, 5. 5 plus 12j. Okay, so here what you get? 5 plus 12j minus 3 square will be plus 9, and then the conjugate 5 minus 12j. This is the answer for yk. Okay. Right, 5 plus 25, 5 plus 12j, 9 and 5 minus 12j. No, Ashutosh, nothing like that. Specify your doubt. Which point? Okay. So this is what is the fifth part of the question. This is what is the fifth part of the question. Okay. Sixth one, DFT of Yn equal to x square n. Now what is x square n? What is x square n? Number 6. Okay. Yn equal to x square n. Okay. Now Sanju, don't do that. I'll tell you why. Because what I'm targeting right now is the property based question. Okay, property based question. See, normally, in any of the questions, see, Sanju, I'll tell you like this. One question is separate. Given xn, find the DFT. Now, whether you talk about second or third, what will be the theme of these questions? What will be the theme of these questions? The theme is, if there is a signal xn, which is not given now, suppose. If there is a signal xn, whose DFT is given to you directly? Whose DFT is given to you directly? Then, what is the DFT of x minus n? Or what is the DFT of xn minus 2? Then you have to use property only, na? Again, if the signal is given, then okay, you can shift or you can fold and again calculate the 4-point DFT by matrix. That is okay. That is okay. One part is okay, Sanju. But most likely when it is, such question, it is property based question. Now I hide xn, but I Hello, 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 hello. Okay, dear. Yeah, I think it should be fine now. Okay, yeah, there was some battery issue, but now it is fine. Let's continue. Okay, let's continue. Okay. Okay, let's continue now. I think it should be fine now. Okay, yeah, there was some battery. Yeah, looks good. Just a second. Right. So let's see, what are the things you are referring now? Shiva Prasad, modern nothing means circular folding. Like I explained you circular folding in time, what I have done, third question means, okay, x minus n has the DFT x minus k. Okay, so we don't have to create x minus n here. What I was telling you that these are property question. In such case, xn not given, xk given. So you have to fold x minus k. Okay, you have to create x minus k only. And how do we fold? Circular folding is always about the n by 2 point. Okay, about the n by 2 point. N by 2 here will be 2 because n is 4. Okay, and what is the role of a mirror? Suppose this is a mirror, you have to fold about this. So this value come to the left value goes to the right. That is what I have done. Like circular folding I have explained you separately, I have implemented here. That's it. Okay, clear, Shiva Prasad? Okay, so that mod n is the representation of, okay, mod n is the representation of, okay, right, that is not remainder. Okay, the mod n is actually the representation of circular folding and circular shifting operation. Clear now? Okay, yes. Okay, don't treat it as some, like we normally do in division, some remainder calculation. No, it is the representation of circular and folding and circular shifting. Correct? Okay, now next question. Yeah, where we were on to the sixth case, yn equal to x square n. And what is x square n? Is xn into the xn. Okay, so what is yk? Multiplication in time is convolution in frequency. Okay, 1 upon n. Convolution of what? Xk with xk only. Same signal multiplied to same DFTs you have to take. 1 upon n. Xk circular convolution xk. Okay. If it is 8-bit, Divya Lakshmi, just watch the previous part of the video. For 8 also how to mirror I have explained you. The mirror has to be at n by 2 point. I have explained you 4 point and 8 point folding. I have explained you previously. So you can watch the video once again if you have missed the earlier part. What is the n here? 1 by 4. But what is the result of the circular convolution? Xk circular convolution xk. Xk circular convolution xk. So what is the xk? I'll write down here 5. This was 3 plus 2j minus 3 and 3 minus 2j. This is again 5, 3 plus 2j minus 3 and 3 minus 2j. Now let's do these calculations carefully. Okay, right. The first part, the first row, multiply by 5. 5 into 5, 25. Then 5 into 3, 15 plus 5 to 10. 15 plus 10j. 5 into minus 3, minus 15. And then this is 15 minus 10j. Now I will multiply by 3 plus 2j. 3 plus 2j into 5, this is simple. Okay, 15 plus 10j again. Okay, 3 plus 2j, 3 plus 2j. So it is the square of 3 plus 2j. Somewhere we calculated, so 5 plus 2j. 3 plus 2j into 3 plus 2j. 5 plus 2j. Then multiply by minus 3. So minus 9 and minus 6j. Okay, and then 3 plus 2j with 3 minus 2j. Okay, what is this multiplication separately? 3 plus 2j, when you multiply by 3 minus 2j, it's going to be 3 square minus a square minus b square, but j square is minus 1. So it will become 3 square plus 2 square. That is 13. That is 13. So next number here 13, but you circular shift and bring it here. Okay, then multiply by minus 3. Minus 3 into 5, minus 15. minus 3 into the above element to minus of 6, minus of 9 only, correct, minus 9 and minus 6j. Minus 3 into minus 3 plus 9, and then minus 3 into 3 minus 9 and plus 6j. Okay, then these elements 9 and minus 9 plus 6j, I circularly fold and circularly shift and bring it here. Then multiply by 3 minus 2j into 5. Okay, so that becomes 15 and minus 10j. 3 minus 2j, 3 plus 2j, same, 13. Okay, 3 minus 2j into minus 3, so minus of 9, minus 3 into minus 2 plus 6j. Minus 3 to minus 2, correct. And 3 minus 2j, 3 minus 2j will be, when you take the square, 15 minus 10j. It was correct only, na? Correct. It is here to be written here. Sorry, 15 minus 12j. Correct. Rest is correct. Just check the calculation once. Okay. Just check the calculation once. Okay. So this is 25 and 13, 38 plus 9 looks like 47. Okay. Just keep confirming with the calculation. Real part 15, 15, 30 minus 9, 21 and 10, 10 and 6 plus 26j. Here it is minus 15, that becomes minus 30 and plus 5. So minus 25 and plus 12j and, oh sorry, I forgot to do the circular shifting on the last case. First I will bring the 13 here, minus 9 plus 6j and 15 minus 12j. 15 and minus of 12j. Now that is correct. Now let me add again. Okay, so how much it is? 25 plus 9, 34 and 34 plus this is further 26. So this is 60. Okay, then 15 minus 9, 6 and 6 and 6, 12. Okay, 10, 6, 16, 10, 6 again 16, 32j. Now this is minus 15, 15, 15 cancel. So minus of 10. Okay, hope the calculations have gone right. Looks like correct only. No, if this was 5 plus 2j, this is 5 minus 2j. This calculation has gone wrong. This is 5 minus 2j. Here there is a correction. Yeah. So now minus 15 and 5 minus 10 and again minus 10. So minus 20 and minus 20 and only minus 20. That's it. Only minus 20 will come. Yeah, perfect. That is perfect. And now 15 and minus 9 again 6, 6, 6, 12 and this is minus 32j. Okay. Yeah, that is the correct answer now. That is the correct answer. Placing down the value of circular convolution here. Okay, which is 60 and next value is 12 plus 32j. Okay, minus 20 and 12 minus 32j. Okay, so the answer is dividing by 4, so 15 and then 3 plus 8j minus of 5 and 3 minus 8j. This is what is the answer that should be coming up for YK. Check the calculation part once again. Check the calculation part on your own also once again. Okay? Just check the calculation part once again. Okay, fine. Now let's go to the next question. What is the seventh part? Energy of x. And see, if the time domain signal is given, then there is no Fourier transform required here. Okay, this is just to show you the Parseval's result that you can calculate energy in both the domain. Okay, let me show you in both the domain here. But in the question, any one data will be given to you. Okay, so what is the xn now? Coming to the seventh part of the question now. Okay, if I take xn, okay, which is given to me as 2, 1, minus 1 and 3, right? This is what is the signal given to me. 2, 1, minus 1 and 3, correct? This is what is the xn given to me. Okay, so what is the energy of the signal in the time domain? It's a real signal, so we can directly write summation of xn square. Okay, so summation of the square of the signal. Okay, summation of the square of the signal. 2 square 4, 1 square 1, minus 1 square again 1 and 3 square is 9. This is total 15. Correct, this is 15. But if you take the xk, okay, see I'm telling you any one data will be given to you. Okay, if xn given, this is the regular formula, then there is no Fourier transform required here. Okay, but Okay, if the xk is given to you, what is the xk? Right now we calculated, but suppose that xk is directly given to you. So what is the xk? We have calculated 5, 3 plus 2j minus 3 and 3 minus 2j. Then what is the energy in the frequency domain? It is given by the formula 1 upon n summation of modulus xk whole square. Okay, for all values of k equal to 0 to n minus 1. Okay, so 1 upon n, that is 1 upon 4, n is 4. Summation of modulus xk whole square. That means if you take any complex number, first take the magnitude of the complex number. Okay, magnitude of the complex number. See, 5 is anyways real, so 5 squared 25. Then, what is modulus of 3 plus 2j? Under root of 3 square plus 2 square, but when you take the square, under root will cancel. So it is 3 square plus 2 square. Then next, minus 3 square is 9 only. Okay, and then 3 minus 2j, magnitude 3 square plus 2 square only. No under root required because anyways I'm going to do the square. Now see the calculation, it should match with our previous answer. Okay, so it is 25 and then 3 square plus 2 square is 13 plus 9 and again 13. Okay, so total 34. Yeah, 1 by 4 times 60, correct answer. 1 by 4 times 60 and that is equal to 15. That is equal to 15. Is equal to 15. That's it. Done. That is equal to 15. Okay. So, using this question, we have done, actually 6-7 different parts out of the same data. We have calculated a DFT also, and we have done some property analysis, circular shifting, circular folding. Where circular shifting, circular folding, I explained you separately also. Then there is this time expansion. There is no time compression property. There is only expansion property that can be generalized. Okay, then this is the list of property that I have already gone through. The properties I have explained to you. Okay, all properties were discussed. Okay, yeah, this was a question on convolution. This was also discussed separately, correct? This was also the question on convolution, circular convolution only. Okay, that was discussed separately. Okay, now let's take another question here. Okay, have a look into this next question. Okay, a GATE 16 2 marks question. Right, have a look into this question. The DFT, the discrete Fourier transform of the 4-point sequence xn, x0, x1, x2, x3, okay, 3, 2, 3, 4 is xk, which is 12, 2j, 0, minus 2j. 12, 2j, 0, minus 2j. Okay, if x1k is the DFT of 12-point sequence x1n given to you, what is modulus x1 8 upon x1 11? Modulus of x1 8 upon x1 11. See here, dear, now understand. Okay, xn is given to you 3, 2, 3, 4 and it has some DFT which is already given to you. 12, 2j, 0, minus 2j. You know you can calculate the DFT of this, but they have given. They have given. So somehow it is property. It's not on DFT calculation. If x1k is the DFT of 12-point sequence x1n. Now see, what is x1n? Okay, 3, 2, 3, 4. See, 3, 2, 3, 4 appears here. So x1n, if you talk about the non-zero values, they are the same as in the signal xn, that is 3, 2, 3, 4. Only between every two value, 3, 2, 3, 4, between every two consecutive values, twice zeros have come. And that comes when you expand the DT signal. When you expand the DT signal, okay, expand by how much? So what I am only assuming is the basics of signals you know. Whether it is CT or DT, you should know the compression and expansion of signal. This is expansion of a signal 3 times. x1n is nothing but x of n by 3. X of n by 3. See here. Okay, if I write down the time values, this is 0, 1, 2, 3. And if you write down the time values here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Total 12 samples are given. Whatever is the value at 0, 1, 2, 3, 0 remains at 0. Okay, value at 1 goes to 3, value at 2 goes to 6, value at 3 goes to 9. Okay, that is what expansion is. Okay, that is what expansion it is. It is an expansion case. Yes, Shiva Prasad, correct. It is a expansion case, x of n by 3. And then what is the time scale expansion DFT property? If you solve it this way, it is simple. Okay, so then what should be x1k? What should be x1k? x1k is the DFT of this x1n. Time expansion, DFT will be replicated. How many times? 3 times. Okay, it is going to be xk, xk, another xk. 3 times replica because it is expansion by 3. Okay, it is expansion by 3. So xk is given to us. Now I'll just replicate it. 12 2j 0 minus 2j. Perfect. Again 12 2j 0 minus 2j. Again 12 2j 0 minus 2j. Now, what is the range of k? K also starts from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What I am interested in? x1 8 upon x1 11. x1 8 upon x1 11. So this value, dear, magnitude of x1 8 divided by x1 11, so that is 12, is divided by minus 2j. Okay, so magnitude wise it is 12 by 2. Answer is 6. 6. Yes, Ashtosha, the very correct answer. It is going to be 6. It is the very correct answer. That is equal to the 6. Okay. Right. Okay. Next question. Simple one. Okay, 2 marks, but simple. See, basic understanding of signals if you have, because I have seen some students solving this question by taking the DFT of this 12-point signal. See, by solving a DFT of 12-point signal, you will be taking a lot of time. Okay, you don't want to solve entire DFT. You only want two values, k equal to 8, k equal to 11. Still, if you solve by two values also separately by DFT formula, will be much more time taking. This is simple. This is simple, but that basic understanding of signal was required. Okay, that yeah, it is the given signal is nothing but the expanded version of the original signal. If that relation is there, okay, then your calculation is there. Because if you are separately calculating DFT of this, then why this is given? It was not required. It is given so that you can use it, and I used it. It is just replica 1, 2, 3 times because expansion by 3. Next question, GATE 18 2 marks question. Again, if you understand what is required, see, there is a DFT given. First of all, it's a 2-mark question, good one. Okay, approach is very simple, question is good. Okay, xk is equal to k plus 1, 0 less than equal to k less than equal to 7. Let this be the 8-point DFT of a sequence xn. Okay, xk is k plus 1. Okay, the DFT is given of a sequence xn, and this is the DFT formula which we already know. They have given the DFT formula. What is the value correct up to 2 decimal places of summation x to n? See what they want. Let me write that first. Okay, what they want? They are looking for summation of x to n from n equal to 0 to 3. So once I open this for n equal to 0 to 3, the first is x0. For n equal to 1, x of 2. For n equal to 2, x of 4. And for n equal to 3, it is x of 6. x0 plus x2 plus x4 plus x6. x0 plus x2 plus x4 plus x6. This is what is the answer. x0 plus x2 plus x4 plus x6, correct? This is what I want actually. Okay, that means I want only alternate values. Okay, only alternate values. We have a formula where alternate plus minus come. Let's try to use it. The first and central ordinate. The first and central ordinate. Okay, dear, what is the first ordinate formula? x0. The first ordinate is given by summation of all x0 plus x1 plus x2 plus x3. 8 point na. Let me write this full. Plus x4 plus x5 plus x6 plus x7, and let us write down capital X1. Sorry, not capital X1. Now let me write down capital X n by 2. Okay, that will be 4. Again, let me highlight what property? First ordinate. This is k equal to 0 and this one is k equal to n by 2. This is a 8 point, so n by 2 becomes 4. Okay, but what happens at every central ordinate? Alternate plus minus will come. That I have generalized already. The x0 minus x1 plus x2 minus x3 plus x4 minus of x5 plus x6 minus of x7, isn't it? Isn't it? Okay, perfect. All right, now you see, Why I have written this pattern? Because the question is asking the summation of alternate terms. Okay, so when you add this here in the second part, there are alternate plus minus. So when you add this, all odd, x1 minus x1 cancel, x3 minus x3 cancel. So when you add these two, now see here, when you add these two, what do you add? X0 plus x4. If you add these two, what is going to be the result? Okay, x1 minus 1, 3 and minus 3, 5 and minus 5, 7 minus 7 will cancel. But what will be obtained? x0 plus x0, that is twice of x0, twice of x2, twice of x4, twice of x6. You want only one time? No problem. If you want only one time, then I should write down the answer as x0 plus x4 whole divided by 2. Whole divided by 2, and Ashutosh has given the correct answer already. Very good. Okay, this is divide by 2. Now what is x0? Any xk is k plus 1. So what is x0? 0 plus 1. What is x4 plus 1? Whole divide by 2. So this is total 6, and 6 by 2, final answer is 3. 6 by 2, final answer is equal to the 3. The final answer is 3. Very correct. Okay, done. Check it out. Check it out. So, approach, practice, is what is important to set your approach. Okay, the approach matters here. The approach matters here. Done, dear? Next question then. Next question. Let's move ahead to the next question. Let us go towards another. This question was already done, the linear and circular convolution relation. Here is the next question. Okay, GATE 23 2 marks question. Have a look into it now. Okay, the DTFT of a signal xn is given to you. X omega is 1 plus cos omega e power minus j omega. Consider that xpn is a periodic signal with period n equal to 5 such that xpn equal to xn for n equal to 0, 1, 2 and is 0 for n equal to 3 and 4. What is xn? That if we want, we can find from x omega. Okay, find from x omega, but no problem. Let's see if it is required. Okay, and xpn is given by summation k equal to n minus 1, k equal to 0 to n minus 1. This is a typo error. ak e power j 2 pi by n kn. Okay, see, what is this actually given to you? Okay, what is this actually given to you? xpn is given by summation k equal to 0 to n minus 1 ak e raised to the power j 2 pi by n. Now what is 2 pi by n? Suppose it is the signal is periodic with period n equal to 5. Okay, if the period n equal to 5, what is the fundamental frequency of the signal? The fundamental frequency is given by 2 pi by n. Okay, so this 2 pi by n, okay, this k and then the 2 pi by n I am writing omega naught into n. What is this? This is nothing but the exponential Fourier series representation. This is nothing but the exponential Fourier series representation. Okay. What do they want? They want the exponential Fourier series coefficient A3. Okay, what is AK? Now, why I am putting this Fourier series coefficient here? See, what is the exponential Fourier series coefficient AK? AK is given by the formula 1 upon n. 1 upon n. See the formula carefully. Summation for one time period, that is n equal to 0 to n minus 1 xn e raised to the power minus j k omega naught n. Okay, this is the exponential Fourier series coefficient. If you are clear about DFT, you are clear about the exponential Fourier series coefficient also. Why? Because I'll repeat this formula. What is AK? What is this AK? This AK is, see here, 1 upon n, summation n equal to 0 to n minus 1 xn e power minus jk omega naught n. E power minus jk omega naught is 2 pi by n into n. So dear, if you just notice this much of the part, forget 1 upon n. What is this equal to? This is nothing but the DFT formula. This is nothing, summation xn e power minus j 2 pi by n into kn. This is nothing but the DFT formula. That means there is a clear-cut relation between the exponential Fourier series coefficients and DFT. Mathematically, they are related, and we can write down any exponential Fourier series coefficient ak as 1 upon n xk. So if you know to calculate xk, you know to calculate ak also. Simple. Okay, simple. Okay, but what is xk here? What is xk here? That is not given. X omega is given. Okay, what is given? X omega is given. DTFT is given. DTFT x of omega 1 plus cos omega e power minus j omega. Okay, can you convert DTFT directly to the DFT? Why not? We started the lecture by that only, converting the frequency into discrete frequency. What is the DFT? X of omega k, or we simply call it as x of k. What do we replace? Okay, we replace omega by omega k, and that omega k is 2 pi by n into k, where n here is 5. N for this question is 5. Okay, so 1 plus cos omega, that is cos 2 pi by 5 into k, into e power minus j 2 pi by 5 into k. This is the DFT obtained. Done. This is the DFT of the question actually. This is the DFT of the given signal. Now the question is asking you, what is the value of the Fourier series coefficient A3? Okay, what is the value of the Fourier series coefficient A3? So A3 should be 1 by n of x3. Okay, or 1 by 5 of x3. N is 5 here. And not only this one, they are only asking the magnitude. So 1 by 5 magnitude of x3. 1 by 5 magnitude. What should be x3? Put down x3. 1 plus cos 2 pi by 5 into 3 multiplied by e power minus j 2 pi by 5 into 3. But because I want magnitude, the magnitude of e power j theta is always 1. Okay, so answer is simply 1 upon 5, 1 plus cos of 2 pi by 5 into 3, so 6 pi by 5. The magnitude of e power j theta will be 1. The magnitude of the e power j theta will be equal to the 1. So what is the answer? Let me calculate. Dividing by 5, 0.038. 0.038 on dividing by 5, that is what the final answer is. Simple. Correct. Okay. Next question, dear. Next question. Okay. Now, next question again. Okay, this question is recently asked just on the 1st February, GATE 2025, instrumentation branch, 2 marks, okay, which was conducted just this 1st February. The question is given a signal xn 1, 2, 2, 4 and it has the DTFT x e power j omega. Now let omega k, they have called the omega by this symbol, omega k 2 pi by 3 into k, and then let yk be x e power j omega k. That means in the x omega, you convert omega to omega k, you are converting to DFT, and suppose that DFT is yk, find y0, small y0. Okay, see here. Can we calculate the DFT of this signal? Yes, we can. We can calculate the DFT of this signal. Okay, this is the, DTFT. First, let me start with the DTFT of this question. We can calculate the DTFT of this question. What it is? The DTFT of this x e power j omega, or simply let me call it as x omega, the DTFT formula, summation of xn e power minus j omega n. Okay, for all values of n. So what is that x omega? I'm simply calling it as x omega. So what is the first value of the signal? 1 into e power. Now this is n equal to 0, 1, 2, 3. Na? Okay, so e power 0. The first is going to be e power 0. So that is only 1. Okay, 1 into e power 0. Then next value of the signal is 2. 2 into e power minus j omega, n is 1. Next value of n, 2, and the signal is also 2. So 2 into e power minus j 2 omega, and next is 4 e power minus j 3 omega, n equal to 3. Okay, so what is the x omega? The DTFT, like previous question it was given, here we have calculated 1 plus 2 e power minus j omega plus 2 e power minus j 2 omega and plus 4 e power minus j 3 omega. This is the DFT calculated, DTFT calculated. Clear now? Now, let omega k is equal to 2 pi by 3 into k. That means if they have defined omega k as 2 pi by 3 into k, that means this 3 is the n. Okay, n, the period or the length. Okay, now they say that let yk equal to how much? X e power j omega k. Omega replaced by omega k, or simply x of omega k. Okay, so what is the x omega I already have? Okay, what is the x omega I already have? I want to replace omega k, omega by omega k, that is 2 pi by 3 into k. Now see here. Once again I will write down x omega. Once again I'll write down x omega, right? What is that x omega? What is that x omega? 1 plus 2 e power minus j omega plus 2 e power minus j2 omega plus 4 e power minus j3 omega. This calculated result, I've just copied it again. Okay, then I will create yk. What is yk? X of 2 pi by 3 into k. 2 pi by 3 into k. What is that 2 pi by 3 into k? Place down the omega. 1 plus 2 e power minus j 2 pi by 3 into k plus 2 e power minus j, okay, 2 pi by 3 into k into 2, and next value 4 e power minus j omega 2 pi by 3 into k, and further into 3. Now what about this last term? See here, this 3 get cancelled, so this is e power minus j 2 pi k. Okay, e power minus j 2 pi k, k is an integer. Okay, so cos 2 pi k 1, j sin 2 pi k 0. Okay, so this is going to be 1, and since this is 1, this also becomes the constant 4. So 1 plus 4 will be added. So what is finally the value of yk? See, what is finally going to be the value of yk? What is finally the value of yk? So 1 plus 4 will be actually 5 plus 2 e power minus j 2 pi by 3 into k. Then next is plus 2 e power minus j 2 pi by 3 into k into 2. Okay, and then this 4 is already added with the 5. They already added with the 1, the net result is 5. Okay, now this is the DFT, na? DFT yk actually given by what formula? Actually given by summation of yn. Listen to me. Summation of y of n e raised to the power minus j 2 pi by n into kn. This is what is the DFT formula. Okay, for n equal to 0 to n minus 1, n minus 1 is 2. Okay, n minus 1 is 2 here. Okay, 0 to 2 and n minus n equal to 3. Na? So when you open this summation, see n equal to 0, the first term is y0. Okay, then and n anything e power 0 will be 1. Next term, what will you write? You will write next one as y1 e raised to the power minus j 2 pi by 3 into k, n equal to 1. Na? Better, I think I should write it here. Okay, just for a clear-cut comparison, I am writing this whole expansion. The first will be y0. Okay, then next term, y of 1 e power minus j 2 pi by n, n is 3 into k, and next term will be y of 2 e power minus j 2 pi by 3 into k into n equal to 2. Correct, na? So when you compare this yk and what I have obtained, you get your answer. This is y0. Okay, so the answer, the question is asking y0, small y0, the answer is 5. Okay, in fact, if they ask what is y1, so y1 e power minus j 2 pi by 3 is multiplied by 1. This was 1 or 2, I think. This was 2, no problem. I'll write this 2. This was 2, and next is also 2. So y1 is 2 and y2 is also 2. But the question was y0, so that's what our answer is. Recently asked this question in the instrumentation. Okay, fine. Next question. Okay. Next question. Just the previous year, GATE 2024. Good question for 2 marks. Good question for 2 marks. No, this is what is the best method Ashutosh I'll suggest for the previous question. Okay. The relationship between any n-length sequence xn and the corresponding endpoint DFT xk is defined as xk equal to f of xn, the DFT, the Fourier transform of xn. Okay. Now, another sequence yn is formed by how? See, f of xn by taking 4 times Fourier transform. And whenever you want to take the Fourier transform of Fourier transform, you will think about duality property. F of xn. Now, if the signal xn is 1, 2, 1, 3, find the value of capital Y0. Capital Y0. See, duality. F of. See, I'll solve the duality very clearly. If xn has the DFT xk. Okay, what is this xk? This xk itself, okay, this xk itself is known as the first Fourier transform. And I need to take 4 Fourier transforms, clear? Okay, so this is the first DFT, I would say. First Fourier transform. Okay, now I will apply duality. Now, if I apply duality, okay, Fourier transform of Fourier transform, so I convert this capital X function into time, capital Xn. This will have how much DFT? Nx of minus n. Nx of minus n, correct? K equal to n and n equal to minus k. Okay. So now let's understand this way. Suppose this is some signal. Suppose this is some signal x1n. Okay, it has some DFT x1k. Okay, and this DFT is the DFT of x1n. X1n is capital Xn, which was already a DFT. So this is DFT of DFT. That is second DFT, second Fourier transform. Okay, I need to do this 4 times. Okay, so now this is another Fourier transform pair. X1n, DFT x1k. Again apply the duality. K replaced by n. So capital X1n will have how much DFT? N small x, small x1. Okay, where this n will be replaced by minus k. Okay, now suppose this capital X1n is another signal x2n. It has some, what should be DFT of x2n? Some DFT x2k. Okay, and this EFT is the third DFT. So one more time and we are done. This is the third Fourier transform. Keep patience and understand. Now one more time. Again duality. Convert this k to n. So capital X2n. This will have the DFT, what? N, small x2. What is the time function? Small x2. And replace n by minus k. So small x2 minus k. And this is the fourth Fourier transform. And the fourth Fourier transform actually should be the signal yn. Okay, should be the signal yn. Okay, now what is this fourth Fourier transform? Let me simplify it. N x2 minus k. Now dear, let me simplify it here. What is x2? What is small x2? See here, what is small x2n? I have substituted this in place of capital X1n. Okay, small x2 means capital X1. Small x2 means capital X1. So capital X1 minus k. Now what is capital X1? Okay. Yeah, capital X1 is here. Capital X1 is the DFT of X1n. Okay, X1n is capital Xn. So what is the DFT? Nx minus n. So what is capital X1 minus k? See here, any doubt you ask me then. See, this is X1k. What is X1k? Nx minus n. Okay, so what is x of minus k? X1 of minus k. So if you place minus k here, folding in time is folding in frequency. So minus k here, so here it should be plus n. So capital N and x of plus n. And what is the fourth DFT? They call this fourth DFT, where is that question, as yn. Okay, that means, so my signal y of n is equal to how much? N into n, that is n square xn. Okay, n square xn. My signal yn is n square xn. Okay, now see. Okay, what is the signal xn? Signal xn has been given to us. Where is the signal xn? 1, 2, 1, 3. 1, 2, 1, 3. Correct. What is the signal yn? The signal yn is n square xn. N square means 16. N is 4. 4 square xn, or that is 16 times xn. 1, 2, 1, 3. And if you take 16 inside, it becomes 16, 16, 2, 32, 16, 1, 16, 16, 3, 48. Now the question is asking you, okay, what is capital Y0? 0. 0 means k equal to 0. And first ordinate property, what is the first ordinate property? Okay, summation of yn, all values are added. First ordinate and central ordinate. First means all added, central ordinate means alternate plus minus. So if you add all 16 and 32 and 16 and 48, net result, this is also 32, 32, 32, 64, 64 and 48 should become 14, 2 less 112. 112. Perfect. The correct answer for the question is 112. A duality. Okay, a full duality demonstration, and final answer 1, 1, 2. Okay. 4 times Fourier transform. 1 Fourier transform pair is already represented. Okay, so 3 times duality. 3 times duality. I told you during the duality property also, whenever you need to take the transform of transform, Fourier transform of Fourier transform, so you'll apply duality. Okay, you will apply duality. You have applied the duality once here. Then you have applied duality where? Once here. And then you have applied duality finally once here. 3 times duality was applied. Okay. And the final answer is 112. Okay. Final answer 112. And based on this duality, I think I will make the password for today's PDF. I'll share you the PDF in my Telegram group. Okay. I'll share you the PDF in my Telegram group. Which Telegram group? I'll let you know. If you're not connected, you can be connected onto it. You can be connected onto it. This one. This is where the PDF will be shared to you. Okay, but the PDF is password protected for a simple reason. Those who have dedicatedly watched, they are actually in the need of notes. Okay, so the entire PDF with all questions, theory, solutions will be shared in my Telegram. There will be a small password protection dual, DUAL, everything in small. Okay, so you can access the PDF by putting this password, DUAL, everything in small. DUAL, everything in the small. All right, guys. So yeah, that's it from my end. Again, a quick reminder that for GATE 26 and GATE 27, if you're preparing, or if you're juniors, friends, anybody interested in preparing, and if you want the online live course of OHM, 8th of February, the batch has recently started with the 1 year GATE 26 fee 19,999, with the 2 year GATE 27 fee 28,999. And yes, if you can really travel down to Hyderabad, or if you stay in Hyderabad or around Hyderabad, you can actually take the advantage of studying offline also, face to face in front of faculty, competitive atmosphere within hundreds of students. And the first regular offline course for GATE 26 for EE and EC both will start from 24th of February. That is after the commencement of the all GATE examinations are over. The fee is currently priced at 54,999. At the same time, if you are any previous home student, or if you belong to IIT, NIT, triple ITs, or any state government colleges, there are special benefits for you. Right, dear? Okay. Other than the live courses, there are also online pre-recorded courses for GATE 26. Okay, for GATE 26, you can purchase the pre-recorded courses so that you learn at any time, at anywhere. Okay, timing also will be totally flexible to you because it is pre-recorded. There are different modules: 3 months, 6 months, and 9 months, and 12 months validity. The fee is mentioned in front of you. Okay, all these pre-recorded courses available on the OHM Online Plus app. Okay, whose QR code is attached. If you want, you can directly download it. Okay. Right. Okay. Yeah, definitely, Manaswi. You can contact me in Telegram in that case. Okay. For the GATE 26, and if you're looking for the long-term GATE 27, so you can again have the pre-recorded courses with larger validity, that is 18 months and 24 months validity. Okay. And there are also online pre-recorded lecture courses for the AE. Okay, if you are willing to prepare for AE, any of the AE exams, okay, the Transco, Discoms, or AEE exams as well. Okay, so there are 3 months, 6 months, and 9 months validity modules available again on the platform OHM Online Plus app. All right, that's it, guys. So yeah, bye bye. Thank you. Stay safe and do take care of yourself.